All right, now your systemic veins and venules and such, these are areas that we refer to as a reservoir. The blood is there. It's not actively being pumped around the body. It's kind of kept in reserve and such. And when you need extra blood flow to carry more oxygen, more nutrients to a tissue, to get rid of waste from a tissue, then these reservoirs will move the blood into the circulatory system and such. So, and the need could be from those things listed there. Either you're exercising, doing something, fight or flight, or you have a major bleed from an area and you're losing blood, pressure's going down. So the major reservoirs, the liver, the spleen, and the skin and such. And I'll bring the skin back in later and such when we talk about a shock and such. So now once it's in the capillaries, once it's through there and such, how does it move, right? What moves? And so you need the fluid, the liquid, the water, with those things dissolved in the water, the glucose, the oxygen and such, well, the glucose and all, to move, the nutrients and such to move. The oxygen is going to move because of other reasons. I believe we already covered those and such. Now, what doesn't leave, what you don't want to leave, are the proteins found in the plasma, and then, of course, your blood cells, your red blood cells, white blood cells, platelets, the formed elements, and all. So, how does it move? Diffusion is always a good choice because you don't spend any energy. But for diffusion to work, you have to have a concentration gradient. So you have to have a high concentration on one side, a low concentration on the other. If you don't have that, things don't move that fast and such. So facilitated diffusion, you might have a protein channel that just allows chloride to move, or just allows sodium to move. That'd be a type of facilitated diffusion. You can see what diffuses right there, and also really most anything dissolved in the plasma will diffuse. Large proteins will not, and you don't want them to. That'd be like an immunoglobulin, albumin, and such antibodies. Those are your large proteins and all. So some things can be moved across, brought in, and you'll see that term penocytosis. You remember that, cell drinking. So the liquids and such are brought in, a little bitty vesicles formed, and then it moves across in the cell itself, that outer cell, then into the other space and such. Insulin will do this. Antibodies crossing the placenta and such will do this as well. So some examples. But the best way to get things in and out is through this process right here, bulk flow. And material will be moved from the artery side in to the interstitial space, and then from the interstitial space to the venule side, both in the bulk flow. It moves things in, moves things out of this capillary bed. What causes the bulk flow? Pressure. So you have this fluid moving from a high pressure to a low pressure. Why is it better? It's just faster. That blood's always flowing. It's just faster and such. This allows for some filtration to take place, but we need to really think about when this happens, we really need a good reabsorption. And that's where the proteins in the plasma really comes into effect on that reabsorption rate right there. So oxygen moves across, your glucose moves across, your sodium moves across, the carbon dioxide moves, the waste moves. It just really helps. It's really fast and such. So it keeps your blood volumes and your interstitial fluid volumes in check and such. Too much interstitial fluid, and we call that edema. So what is really involved in it? It is your blood pressure. That's the big part of it right there. Now, what pulls the fluid from the tissue back into the veins, into the venous side? That is your colloidal osmotic pressure. So that's done, and we have to, I say a little trick, water follows protein. You're going to say that to yourself when we do the kidneys and other things. Water follows sodium, water follows potassium, water follows proteins. And so you need those proteins. And wherever the proteins are found, that's going to want to pull the water and such. That is the colloidal osmotic pressure. The dominant force, though, is your blood pressure. Your blood hydrostatic. Hydrostatic is the fluid pressure. You have an interstitial fluid osmotic pressure. But that's not very large because it doesn't have very many proteins and such in that space. But it's the proteins in the blood, in the capillary. See, the water's out, and all you have left is the red blood cells, white blood cells, the large proteins, and the platelets. And those proteins encourage the fluid to move from the interstitial space back and such. So that is your blood colloid osmotic pressure, and that has to be there in order for to keep the fluids out of that space and such. So there is an interstitial fluid hydrostatical pressure right there, and that will also then push. As you push fluid into that space, the pressure builds up, and it pushes the fluid back into the vein side because fluids move high to low. And when you enter the capillary on the arterial side, by the time you get to the venous side, the blood pressure on that venous side should be at or near zero. But then the colloidal osmotic pressure and this interstitial fluid pressure moves liquids back into that, and then that slowly causes the blood pressure to increase. So the blood pressure in your right atrium should be at or near zero. So you have to get your venous side above that in order for the blood to flow back to the heart. Fluids only move from high pressure to low pressure. What gets filtered should get reabsorbed, right? That's what you want. That's your Starling's law of capillaries and such. It doesn't always work. So of all of the fluid that gets filtered into the space, about 10% is left behind. So that part has to get picked up by the lymphatic system. So that lymphatic system is what we'll talk about in the next upcoming videos and such once we get out of the circulatory system. But it's also how in this interstitial space, you can have bacteria that gets picked up by the lymphatic. You can have viruses which get picked up and moved to the lymphatic. You can have cancerous cells which gets picked up and moved back to the lymphatic. The lymphatic picks up all of this excess fluid with its baggage and runs it through a series of vessels that have little forts called nodes along the way, but that eventually all gets back to either your right subclavian vein or the biggest one is in your left subclavian vein. And it puts all of that fluid back into the circulatory system. It picks up excess fluid, puts it back in the circulatory system. When you have excess fluid in that tissue space or in that interstitial space, that is edema. What causes edema? You can see right there, of course, high blood pressure can cause that. If the capillaries are extra leaky and such, it'll allow proteins to escape, which then pulls water and such. It could also be due to not having enough proteins in the plasma portion of the blood. And so why would you not have that? Malnutrition, not eating correctly. You don't have enough protein in your blood. Excessive burns, kidney diseases and such. Those things will lower your blood's colloidal osmotic pressure, which would then discourage reabsorption, which would then you would see or observe as edema. You could also get it by blocking the lymph. That happens. It can happen quite easily and such. There's a parasite that will do that. Not found in our neck of the woods, but it's out there. Other things that affect this is hemodynamics and such. This is the blood flow, what affects these things and such. And of course, what's the pump is the heart, and then how much is it pumping? So how many beats per minute, and then how much fluid is pushed out with each beat and such. Fighting those is your blood pressure and your resistance and such. So they also affect the flow. So we know what blood pressure is. It's the amount of force that when the ventricles contract, that's systole or systolic pressure. We can measure that, and we use a sphygmomanometer, It's in the olden days, it was a column of mercury, and you would say, how high is that column of mercury? And they would measure it in millimeters. And so in a person, when the ventricles contracted, that column of mercury would be held at about 120 millimeters in height. So you would have 120 millimeters of mercury, or mmHg. And then when the ventricles relax, there's still enough pressure in there to hold that column of mercury at a height of 80 millimeters, or 80 millimeters of mercury. Try saying millimeters of mercury real fast 3 times, and you'll very quickly understand why I drop it. Every measurement that you take must have a number and a unit. And in this case of blood pressure, the units are understood. So we say 120 over 80. We know that it's 120 millimeters of mercury over 80 millimeters of mercury. Those units are understood. You can do a mean arterial blood pressure. You take the diastolic, which is the bottom number, and then you add it to the systolic blood pressure minus the diastolic. So you do a difference between 120 and 80. You take a third of that, then you add it to the lower number, and that gives you an average. Most people just give you the 120 over 80. They give you that number, and everybody's happy. If there's no change in resistance, and that means the blood vessels are not constricting or the blood vessels are not relaxing. If there's no resistance change as such, then when the heart beats more, blood pressure goes up. If the heart doesn't beat, blood pressure goes down. As you move away from the heart, the blood pressure gets lower and lower gradually as such until you get to the venous side, the venial side, and then it goes to 0. Then it starts picking back up. All because you're moving the blood there in the venous side. But the largest vessel with the lowest pressure should be the vena cava. But it still has to have a pressure higher than the right atrium. Keep that in mind. That right atrium has to be at or near 0. There has to be that change in difference of pressure, that gradient in pressure for the fluids to move. If all the pressures are the same, blood flow stops. Resistance. This is basically friction, and that is the blood rubbing on the sides of the vessel. So if you have a larger lumen, you have less resistance. You have a smaller lumen, you have greater resistance. So vasoconstriction, you tighten it down, the lumen becomes smaller, resistance goes up. Vasodilation, you relax, the smooth muscle relaxes, the lumen gets larger, and then resistance decreases. The thickness of the blood. This is your viscosity of your blood and such. And that's your hematocrit. Remember, a normal hematocrit should be 45 in an adult. But it also has to do with the blood cells in relationship to the plasma. So when you're dehydrated, you're not drinking, you increase your viscosity, which then increases your resistance, which then affects your blood pressure. You could have, on the other end, you could have a loss of red blood cells due to anemia, or maybe you have a bleed somewhere, or you have decreased plasma in there, malnourished and such. So your blood would be thinner, be able to flow more easily, but yet you would have a decreased velocity or decreased viscosity, if you will. The total length of the vessel has a lot to do with it. So when you think about the arterial side, how long are these vessels from the heart to the capillaries? And when you think about fat, you have to put fat is very vascular. So you put more blood vessels in total length through that and such. And so excessive fat leads to more capillaries, which leads to a greater resistance, which leads to a higher blood pressure. All right, we're going to quit.